Thank you very much for the introduction. So this is going to be the second part of the lecture on numerical ODEs, if you would like. The outline of today is this lecture is I'm going to cover two things without going too much into the details. As the building block of these quantum subroutines we already have learned last time. So I'm going to briefly mention what are the Hamiltonian simulation problem when the Hamiltonian is time dependent. So last time we have talked about everything about time independent Hamiltonian. What if the Hamiltonian is time dependent? What are the corresponding algorithms to do that? And then I will discuss about the general linear differential equation that the underlying dynamics may not be unitary and what are the challenges. I will mainly focus on the challenges and then point out possible solutions to that. So this is sort of the outline. So before I go into what I want to do today, this is sort of a revisit of what we covered last time. We defined the problem, we talk about motivation, we have the expected cost, and specifically there are three quantum algorithms that I discussed. Number one is totalization. It uses no NC loss. However, it requires the Hamiltonians has certain form. The second is truncated Taylor series. This is combined with the LCU. So this is the LCU-based approach. The optimal Hamiltonian simulation, which matches the theoretical lower bound, can be used by this QSVT technique. I think it's worth to say that all of these algorithms, all of these block encoding related algorithms, you need to do some form of OAA, which is what I mentioned in the end yesterday, this obvious amplitude amplification. So I think before I discuss about the new things, I think it can be beneficial just to do a little bit of exercise or revisit of these three crucial techniques that we saw last time, and we will also use them for today's lecture. So the first one is this QSVT. So I just want to revisit that the QSVT in the simplest form is basically doing the following. We're given a matrix A, and we know that any matrix can be written as its singular value decomposition. And I have alpha, say, is the subnormalization factor of it, that is the upper bound of the spectral norm of A. So if this is the case, well, QSVT is essentially a routine, and the cost is of order D, where D is the degree of this function f. What it is going to do is that for this function f, we're going to define this so-called generalized matrix function. It is precisely defined this way. I'm going to only change this sigma divided by alpha, which is the singular value part, through this function. So I got, after my lecture yesterday, I got a very good question from the audience asking that, well, how do I know what is U? How do I know what is V? How do I know what is sigma? Isn't that very difficult and costly to compute? The beauty of QSVT is that you do not need to know them explicitly. You never use them. So you just pump it. You have a block encoding of A. You just pump it into this QSVT subroutine. It automatically gives you this. And you don't need to have to know what they are. So you do not need a calculation. However, the restrictions is that this function f needs to be bounded by 1. It doesn't need to be bounded by 1 everywhere. It needs to be bounded by 1 in between -1 and +1. You may wonder that why do I care about -1 and +1? The reason is because look at here, the function. The input of the function is really sigma divided by alpha, where sigma is all of the singular values. The bounds, all of the singular values are actually upper bounded by the spectral norm of A. So this guy is upper bounded by the spectral norm of A divided by alpha that is automatically bounded by 1. So as long as in this range it is okay, I don't care about the place elsewhere. And then there's also a restriction, so-called parity, which means it needs to be an odd function, odd polynomial with odd degree, and it needs to be an even polynomial with even degree. We also see if the A is a Hermitian matrix, how can we bypass this parity condition? So I think these are very important things. So now I think it's nice if we just do a little bit of this exercise to get more understanding of this QSVT. I just want people, maybe you can do it quickly or think about it in your mind, that you can please quickly check if alpha equal to 1 for simplicity, and I just take a function as x squared. Please check that these two things actually are not the same. I just want to emphasize that generalized matrix function is really not the same as just a matrix function.
Well, unless the polar part of J is identity.
Yeah, exactly. Yeah, exactly. So why is that? Do anyone want to tell me what I should write here?
That is U sigma F sigma unified F.
And on the right-hand side, what I should have? Unless this guy is an identity, otherwise they do not equal to each other. So this is a very important thing of what QSVT is able to deliver versus what matrix function is typically defined. The second very important routine, which is used across all of the block encoding related Hamiltonian simulation, is this very important thing of OAA. What I said last time is I did a calculation of OAA, and I told you in the end there was this funny term, which is A dagger A, and I said if A is very close to unitary, and then this is almost equivalent to A, and then you get this OAA to work. Now, I think it's a nice exercise if we see it again from this different perspective. I'm not going to say A is close to unitary. For simplicity, that just say, okay, A is unitary. Then what is the singular value of A? Can someone tell me? A is unitary now. What is the singular value of A? 1, great. So now we know that the singular value is 1. So basically what I have is this U, this is 1/2, 1/2, 1/2, and the V dagger. So last time I said OAA is actually equivalent, can be viewed alternatively as doing a QSVP with respect to this odd function. Why is that? Because if you put 1/2 here, you map basically after QSVT all become f of 1/2. What are that? If you put it in, f of 1/2 is 1. So after the mapping, the generalized matrix function will give you U, and all the middles are 1, V dagger. And what is this? This is A. So that's why we are precisely doing this by this OAA. And this is very important that unless A is either unitary or close to a unitary, this can be done. Imagine if you have many singular values that are not necessarily 1, you just use this function, it's not going to work. Are we okay so far? Okay. And the third technique, which is also widely used in Dong's lecture, is this LCU. Just to say that suppose A and B are both unitary, and I want to do this linear combination using a LCU way. Can anyone tell me what should be the subnormalization factor here if I do it in a LCU circuit? The L1 norm of the coefficients, in other words, is the sum of these two. This is what we will get in the denominator. All right, so these are some things are also relevant to what I'm going to talk about today. That's why I think it's helpful if we just revisit a little bit. All right. Now I'm going to move on these sort of new things. So first of all, I'm going to talk about time-dependent Hamiltonian simulation. And we are going to define the problem as what we did before. So I'm going to look at this most generic error metric, which is a worst-case scenario. In other words, if this works, then for arbitrary initial condition, arbitrary observable you gave me, we all have provable guarantee. So now, because the problem is time-dependent, the Hamiltonian H at different time may not commute with each other. That's why the exact solution has a time ordering term, just slightly more complicated than the exponential that we had before. But nevertheless, the story is the same. We want to bound it by epsilon. But before I move on to talk about these algorithms, how we do this time-dependent Hamiltonian simulation, my natural question would be, why should I care? Okay, and why should I care about time-dependent Hamiltonian simulation, right? There are a few things I want to mention. First of all, maybe in your physical experiments or physical system, it has maybe external field, or maybe you want to do some quantum control, then it naturally might have some time dependence. Or we have seen in Dong's lecture today is that if you look at, say, the linear system solvers, we might want to use adiabatic quantum computing to achieve an even better scaling in terms of the kappa. Adiabatic quantum computing is precisely a time-dependent Hamiltonian. There's one more reason. And also, the adiabatic computation can be also used for state preparation purposes. So for all of these applications, even if it's not to simulate physics dynamics, you may still want to use Hamiltonian simulation. But then you might not buy my argument. You might be like, well, I just care about physical dynamics, and my physical system is just time independent. Say, for example, it's molecular dynamics. I'm happy with time independent. Why, if that is the case, why should I care about time dependent system, right? If you have that question, let me just give you an example why you should care. It is actually, if you care about time dependent problems, you can actually, in many cases, get improved scaling. This is one example. For example, you can reform the time-independent Hamiltonian into through the so-called interaction picture, which is a long-celebrated formulation in quantum mechanics, have very long history. The point is that suppose I have a time-independent problem, which has A plus B, where A has a very large norm. So you can imagine if I want to block encode this using whatever technique you want, maybe a LCU, then the norm of A will dominate this block encoding factor. However, what this interaction picture is doing is, before that, the mathematical motivation, for example, might be I can have, say, in the PDE, though this is ODE lecture, but in PDE, maybe I have Laplacian plus potential, where Laplacian is unbounded operator. If you talk about its operator norm is infinity, even if you discretize them, it's going to be very large. However, if you just look at the second term, it might be something that is fairly small. So this one might be dominant. Well, in that case, what we can really utilize is this so-called interacting picture formulation. Mathematically speaking, you can really sort of view it as an integrating factor method. The idea is that suppose e to the IAT is such in a form is what we so-called fast-forwardable, which means that if you evaluate this exponential is almost independent of time t cost, what are the fast-forwardable Hamiltonians? For example, maybe this Hamiltonian is diagonal, or maybe the Hamiltonian is diagonal in the Fourier basis, then you can use QFT, it's still going to be fast-forwardable. If you are lucky enough in that case, then you can reformulate this time-independent problem into a time-dependent one. Okay? And there are the two things are equivalent. You can solve whichever you like. And then you may wonder, like, it doesn't make much sense, because originally I have time-independent problem, which seems to be simpler. Now it becomes time-dependent. Why do I want to do this, right? What I want to highlight is if you look at the spectral norm of this new operator, it's time-dependent. But if you only focus on the spectral norm, can someone tell me what the spectral norm should look like? It's spectral norm of B. You completely get rid of A. So that is larger one, so this is a gaining. And then a further question might be, well, if that is the case, why don't I always, well, what is the challenge? There must be some trade-off. There shouldn't be any free lunch. So the challenge here is really that this new Hamiltonian by itself is oscillating on a very fast scale. You need to make sure you are implementing this time-dependent Hamiltonian in a way do not reintroduce this high time scaling, which is on the scale of A. In other words, in time-dependent Hamiltonian simulation, it's very important feature that people typically really want to acquire is that you want to have log dependence in terms of the derivatives of the Hamiltonian, for example, because the derivative will roughly give you the oscillations that depends on the larger ones, that is A. All right, I hope so far the motivation is clear. We have a time-dependent problem, and the desired feature is we want to have a log dependence on the derivative. Now let's think about how do we simulate this problem. Well, this is an analogy of classically how we simulate ODE, and also analogy to many of the algorithm for time-independent case. So I have a time t, I chop it into small pieces. At each of the time steps, I use a good approximation locally, and then I want to piece everything together. This is basically what we do. And basically, at each of the time step, if you have a numerical integrator that may not be unitary, then you somehow deal with this block encoding business where this alpha is not necessarily equal to 1. For example, maybe this alpha solmization factor is 2, well, then you may wonder, if I piece everything together, wouldn't this 2 become multiplied together? If I have L times steps in total, it becomes 2 times L, which is exponentially large in terms of the number of time steps. However, Hamiltonian simulation, as what we just see, is that we can do this OAA. We can make this block encoding factor, even if it's not 1. We can always make it to 1. And then 1 raising to the L's power, you don't need to worry that much. Are we okay so far? This is very important. When we discuss non-unitary dynamics, we will lose this very nice feature. Okay, so please.
So maybe worth adding that the log dependence on the derivative is truly a quantum feature. There is no obvious classical algorithm that can achieve such a scaling.
Yeah, that's right. That's right. Okay.
I have a question. So before, in that Laplacian plus potential, so what kind of conditions you're assuming on the potential? Like, is it a bounded function? Like, for
example, it's a bounded function. If it's also unbounded, then you may not have the gaining.
What about simple harmonic oscillator? Like,
yeah, actually, the Laplacian plus simple harmonic oscillator, that by itself is diagonalizable. So it's actually a simpler problem. If you cares about maybe this plus a quoted term, and then there are other discussions. But harmonic oscillators are by itself diagonalizable. That's a great question. For Coulomb potential, you actually will not have a gaining using this kind of formulation. You will have a slight gaining. Well, this is the previous interaction picture formulation is not just restricted to unbounded operator. Maybe, for example, in the second quantizations, you will have a gaining versus the first term is roughly of order n to the 4th, where n is the system size, and the second term is n squared. So you will have a polynomial gaining, but not necessarily exponential. Yeah, not necessarily getting rid of the parameter. Thank you. All right. So
talk about harmonic oscillator. That's related to the bosonic problem. It needs to be treated specially, and one of the best work is actually done by Yu and a couple of years ago, Yu and Presco and other people.
Yeah. Okay. So now we know how to piece things together. It's basically by OAA. Then the next question is just what are the corresponding short time integrators? So I will mention briefly these 3 different types of integrator. Number 1 is totalization. This cross means, unfortunately, it do not have this desired feature that we wanted. The second is randomized algorithms. It indeed have the desired feature, but it's actually a sampling algorithm with weak convergence in the mathematical sense. I will mention what I mean later. The third is there is a LCU basis approaches like what we had for time-independent cases. We can truncate a series. There are various different series you can truncate. You can truncate Dyson series. You can truncate magnet series. You can truncate other series. And this will give you a very nice dependence on the derivative. You may wonder, well, I'm missing the QSVT for the time-dependent cases, right? Previously, I have this, I have that, but I also have a QSVT. So unfortunately, up to now, at least from what I know, there is no clean time-dependent QSVT for a general time-dependent matrix H. So that is that will not be included in this discussion. All right. So now I'm going to talk about the totalization. So for totalization, again, it resembles the time-independent case. You need the Hamiltonian to be written in a special form. It needs to be a sum of a number of terms. For example, maybe it's a sum of these 2 terms. Both of them are time-dependent. So actually, what totalization in the time-dependent case is doing in terms of a numerical analysis viewpoint, this is really a quadrature method with rectangular quadrature. It is stating that from this interval I care about, I want to choose 1 point to represent the value of this interval, and I'm just going to integrate that, and this gives me what I want. So since this quadrature is really a loose quadrature, you are just using 1 quadrature point to representing what is going on. So it's not difficult to imagine the derivative actually comes into the cost. So here is a first order total. You may wonder, what if I go to high order? Does that resolve the issue? Unfortunately, it does not resolve the issue. And the proof was given in this paper. You can find over that. All right. So total, well, it doesn't work as what I wanted. Because I'm just picking deterministically 1 point from this interval that I cares about. The very natural question would be, what if I cleverly pick this representative point stochastically? maybe here the operator norm is larger, then I have a higher probability to choosing that. Here it is smaller, I have lower probability. Maybe it will give me a better dependence. Can you do that? The answer is yes, and this corresponding to continuous Q-drift methods and also many of the other methods I listed down below. The essential idea is that, well, for people familiar with quantum formulation, this is a quantum channel, this is the ideal quantum channel, this is the ideal time evolution, and this is exact evolution of what we have. And then correspondingly, we are going to use the Hamiltonian norm of H to serve as a probability function. And then actually what you can do, this is approximation, what you can do is that you, according this probability distribution, you choose a time, and then you only need to evolve it with respect to that specific time. So it will still be a product formula where you multiply in a bunch of unitaries together. So I just want to say that for quantum experts, a quantum audience, this convergence is in the sense of quantum channel in the Diamond norm, and the convergence is a first order convergence. For my mathematical friends, this just equivalent means that this is a stochastic algorithm. This convergence, it has a weak convergence of order 1. This is fairly reasonable because if you think about stochastic algorithms, say Euler, Maruyama, then the strong convergence is 1/2. However, if you think about the weak convergence is 1, it's precisely the same story going on. We have a weak convergence of 1 first order, and this is what we have. All right. And now let's move on to a series truncation. Well, so the previous 2 algorithms is either I use a rectangular quadrature or I use a sampling way of doing this quadrature. You may wonder, well, can I do it more accurately? Well, this is one way. For example, I can expand. This really resembles the Taylor expansion. This is, you can sort of view it as a generalization of Taylor expansion in the time-dependent case. Indeed, if H is time-independent, it reduces to the Euro-Taylor expansion that we already discussed. So what we will have is that we have a bunch of series truncations, and then the ideas would be I have a block encoding of this, block encoding of that, and then I do the multiplications. You counter all of these integrals. What do? You want to use many quadrature points, and then you do a LCU. Because the nice thing about LCU is that you have log dependence on how many terms you are summing. Maybe the terms that you are summing in total is actually dependent on how fast this H is oscillating, but it's just log dependence on that cost. This is precisely how we achieve the desired feature on a very high level. There are various, I just want to mention, Dyson is one case. You can also do a truncated Taylor series, which give you which give you even more desired features such as superconvergence and so on and so forth, but let's not go that far. Well, before I move on, I just want to mention a little bit of how you derive the Dyson series. Maybe for my physics friends, this is natural to you. You immediately know how to do. But for mathematical friends, if you are, if it's the first time you see this kind of things, I just want to say this is really just Picard iteration. So what you do is you first write down the fundamental theorem of calculus, where our calculus students know how to do that. And then it will depend on this U by itself. And then you do the Picard iteration, which means that you reuse this and to plug it in, and well, this T is changed to T1, and then you will have this term. You do it repetitively, and then you will get this series expansion. This is precisely how you derive that. So there's no mysterious whatsoever. All right, are we okay so far? So I have finished my discussion about time-dependent Hamiltonian simulations. I think many of these techniques, you will also hear about them in later, say, workshops, especially in workshop 1. Please.
So since you mentioned Picard iteration converges. So is this Dyson series guaranteed to converge always?
Yeah, that's a great question. So this Dyson series is like a Taylor series. The convergence is that if A is upper bounded by certain constant, this is like the sum is like an exponential, right? So it's indeed convergence if H has an upper bound of alpha. And typically, we are just using this on a shorter time steps, which means that we want to use it such that this operator norm of H times this smaller time step is bounded. So this typically bounded by, say, log of 2. Yeah, please.
So can you go back to your previous PPT?
Yeah.
About the piece order charter. So I'm wondering, so in the complexity, you have the partial T to the piece power. So why it would depend depend on the piece?
Higher derivatives.
Yeah.
Yeah, that's a great question. So if you think about so this is for higher order chorters. You will automatically have a higher order derivative dependence.
For higher order
For
chorters?
higher order chorters. So you might think that, let's see, what is a good way to address?
Yeah, so my question is why does higher order derivative come from the higher order chorter? I'm thinking you might find a better way to approximate the integral than the better formula. Its error will depend on the higher order derivative of h, but I'm not sure like why higher order chorter will also introduce like higher derivative of h.
Higher order, I do not remember the proof immediately, but I think I can discuss with you afterwards. Yeah. Please. Yeah.
Because you're evolving with a specific ht for specific t, right? So, and you need that to represent the evolution for a period of time. So there is some derivative that needs to be taken into account.
Yeah, his question is why higher derivatives? Yeah. Yeah. Jens, please.
So for yesterday, there was this whole design space that we can do time independent this way and this other way and this third way. Here, today, it seems like the design space is much smaller. There's really only one method that you recommend. Is that about right?
I'm talking about all of these different methods. So all of these, I should mention that chorization randomized algorithm and also series LCU-based algorithm are all of the categories of choices that we have. So each of them have different, we have a continuous Q drift, we have hybridized method, we have monocolor method. Each of them covers, but the high level ideas is the following. Either we choose one quadrature, or we choose a random layer quadrature, or we choose many points as a quadrature. This is, but the details algorithm include many more. Yeah. Yeah, thank you for the question. Please.
This is very naive, but why is QSVT not good in it? Like you cannot implement sine and add cosine like time independent and do it many times. Is that the matrix multiplication?
Yeah, so QSVT really works if A is time independent. For example, if you have A can be written with a very special case, say A is a scalar function C of t, maybe, and then multiply another matrix. Well, let's say H. And then you can still, there's still possible ways you can do QSVT. But for general H of t, maybe all of these entries has some time dependence. There's no known way.
Each time sector is time independent, right?
Yeah. It really goes into this maybe 4 lectures of what precisely how QSVT and qubitization works. So that do not quite go through if everything is time dependent. Thank you for the question. Any other? Please.
My question is probably very naive too, but I don't understand when would we use each of these algorithms? Like what are the situations where you use characterization and randomized algorithm?
Yeah, that's a great question. So if you want an algorithm that you don't care, the derivative is bounded, you don't care that much, then maybe you can still use characterization. It is nice because it does not require ancilla qubits. And if you are, for this algorithm, when I say it's first order convergence, in the weak sense, it means that it has linear in the inverse of precision dependence. So for this algorithm, if you are okay with an inverse of precision dependence, maybe the precision you care about is not that small, then you are okay. However, I should mention that for this series truncation, the precision dependence is log. So if you have a very high precision that you want to resolve, maybe this is a better algorithm. Yeah, it's faster. When I say the dependence, I mean the cost. So the previous randomization, the cost in terms of the precision is this scaling. However, the series dependence is this scaling. So this is much faster. This is much smaller compared to that one.
Okay, but then if that is the case, wouldn't you always want to use series truncation LCU based?
may not be the case is because, well, you can imagine I have many terms. I need to first truncate, and then I need to do quadrature to all of these things, and I need to do LCU altogether. And this, throughout all this procedure, you need ancilla qubits, which is not going to be gigantic, but you need ancilla qubits. Versus in the previous product formula cases, you do not need ancilla qubits. So it's become, yeah, practicalities. Yeah, exactly. Thank you for the question. Me? All right, so now I'm going to move on to the general differential equations, which are linear differential equation, but the underlying dynamics is not necessarily unitary. So in this part, I will first give the definition of the task, and then I will spend some time to discuss the challenges. So this, I think if you understand the challenges, it will be a very good learning experience to take as a takeaway. Then I will just briefly address 3 ways to address these challenges. None of the 3 ways is perfect in the sense that none of the 3 ways is 333 proposed by Lin earlier before, but we very much hope that in this all workshop weeks and of maybe workshop weeks we can discuss more about that. All right. Okay. So now I'm going to define the problem. I'm going to focus on homogeneous differential equations. You may wonder, what about inhomogeneous differential equations? Mathematically, we can say inhomogeneous differential equations can be mapped into homogeneous differential equations. Well, this sounds very easy, but quantumly, it's actually much more complicated, more technicalities you can take care of. But I think in my tutorial today, just talking about homogeneous differential equation is sufficient for our purposes to illustrate what are the challenges and the corresponding solutions. So the definition of this problem is that we are given a vector, and we have a time-dependent differential equations, which is linear, and we want to prepare a quantum state. It's because quantum computer only produce a quantum state. We want to prepare a quantum state that is proportional to the solution that I really want. Well, you can write it down in this way. All of these normalization factors just coming from the fact that the solution, the actual differential equations may not be normalized. So similar as the linear system solvers, we are losing this amplitude information. But this is, in the end, a quantum state encoding this information is what we want to get. Well, you may wonder, well, is this problem a hard problem? Well, it's debatable depending on the input model and the output models. But at least we know that Hamiltonian simulation is a special case of this, and Hamiltonian simulation is already BQP hard, which means if you have a generic solvers for this, it is expected to be at least at least the BQP hard if you can do it generically. So this is sort of the argument. Well, now you can see.
At this point, say what's the complexity of the best classical algorithm for solving this problem?
What is the best complexity?
Complexity of the best classical algorithm for solving this problem?
That is not clear. So the argument of BQP hardness that I was mentioning is that BQP hardness is at least is harder than BQP. Well, BQP contains Shor's algorithm, which is integer factoring.
This I understand, but the problem on the board, though, is very concrete. And I know people have been working on this problem for decades.
Yeah.
For the best known classical algorithm for this, your problem, what's the complexity of that algorithm?
Yes. For generic problems, you have polynomial dependence in terms of the system size, which is 2 to the n, right? For generic problem. I'm not saying that for specific case you cannot improve further. But for generic A's, that is what is expected, 2 to the n, polynomial in 2 to the n. Very good question. Thank you. Any other? All right. Then if we look at this problem, it could be, we can sort of rewrite it in an almost Hamiltonian simulation way. Basically, we want to simulate this time ordering operator where there is some integral going on. And then we can just do some, apply to the quantum state that we start with, and we get what we want. All right. Okay. Now I'm ready to talk about the challenges. Let's first think about if I have a linear differential equation, linear ODE, how do we solve it classically? Right? I have some time I want to simulate. I always chop it into small pieces, and each of these small pieces have a time interval that's called delta t, and there are L time steps in total. And I have this from u0 to u1 and u1 to u2 and so on and so forth. right? This is sort of time marching from the previous time step, I go to the next time step. This is used in Hamiltonian simulation for quantum algorithm as well, and this is widely used for nearly all of the, this is the base of all of the differential equation solvers. Now let's look at where could potentially be some problem. Well, in all of these sub-time steps, I'm just going to use some very accurate numerical approximation. I'm going to say this is a numerical integrator. There are various numerical integrators you can use. For example, naively, we can use forward Euler. This is one choice. Or you can use fancier one. Maybe you say, OK, I'm going to use exponential integrators. This is another choice. Well, however, if I want to draw your attention before this line is if I just look at this. Well, you know, what's introduced by Dong yesterday is that quantumly, we have this very important restriction, which is so-called the no-cloning theorem, right? When no-cloning theorem essentially states that there does not exist a generic operation to copy arbitrary two quantum states. So it's not like classical computer, we do Control-C, Control-V, we immediately get another copies of this. Quantumly, there is no generic copy operation to do that. So if you just have this and that, it seems that at each of the time step, it appears, it may not be the case, but it appears that I need two access of the previous time step, right? And then the next time step, how many times I need this time step? I need 2 squared. Suppose you have L time steps in total, how many time steps you need to access your initial state? 2 to the L, where L is number of time step. This is problematic. This is a very huge number. However, you may say, OK, but this is a linear problem. I just make it together, and this becomes a matrix, and I try to do the block encoding. I don't need to worry about no-cloning theorem, right? So far seems to be the case. Let's continue to see then what happens. So you agree with me, I have all of these matrices I want to apply because this underlying dynamics is no longer unitary, so these are not close to unitary, so I will have to do some notion of block encoding. Are we OK so far? Yeah. OK, so now I want to do the block encoding. I want to block encode this. Suppose I have a block encoding of A. Can someone tell me what is the technique, say, on the board that I use to do the block encoding of this guy? LCU, exactly. Then what do you expect to be the subnormalization factor? Exactly. This is the expected subnormalization factor you would expect to get because this is the sum of basically the terms. All right, fine, so far so good. And then each of the time step, for simplicity, I am assuming this A is time independent just for illustration purposes. Then I have each of the time step of block encoding, block encoding, block encoding. I can just use the product of block encoding to create the block encoding of this long time evolution, right? This is very reasonable. Let's try to do that. Then what happens? The subnormalization factor get accumulated, so there are L time steps. Each of this term, by the way, is guaranteed to be larger than 1. It's guaranteed to be larger than 1 because we have 1 plus that. So this means that if you really apply it to the state that you want, you get what you want over here. In the end, there is some part is your solution that is what you want. There's some garbage part. And you need to somehow extract this solution from this quantum state. And this success probability is actually exponentially vanishing in the number of time steps that you have. Okay so far? And this is a precisely exponential vanishing problem. Are we OK? This is really the challenge. That's why you cannot just say, OK, I have a classical. I just put it on a quantum computer. It gave me an exponential speed. That does not work. Well, then, since we are mentioning this success probability, you may immediately want to ask that, it doesn't make sense. Isn't that quantumly, we have this very nice technique, amplitude amplification, which is precisely designed to fix the success probability issue. If I have a success probability that is p, maybe that is low, I can sort of repeat the circuit of order 1 over root of p time. And then I can boost the success probability to almost 1, to omega 1. Isn't that I just do that and it should be fine? Right? This is a very natural question to ask. But then you will realize that amplitude amplification actually requires access to the state that you start with. So now I'm saying that, OK, each of the time step, I do amplitude amplification. I need to repeat the circuit this number of times with this number of access to the state that I start with. And the next time step, I need this square number of states that I start with. So you have L time steps in total. You would count that the number of is this power raising to the L's power. Again, you have an exponentially large number of copies that you need to deal with. Please.
Is it ever so the success probability could change at each time step because the system
that's right. Yeah, that's right.
Is it ever an issue to determine the number of rounds of amplitude amplification at each time step? Because you could do too many rounds and overshoot it, and then your success probability would be really small. So does that also present another challenge?
Yeah, that presents another challenge. That's the take-home message would be you really don't want to do amplitude amplification of this sort at each of the time steps. Yeah, that's a very good question. Please.
I don't really understand why you need multiple copies of your state. Amplitude amplification doesn't destroy the state, right?
Yeah, so how do you do amplitude amplification? You repeat the whole circuit. This circuit evolves in the initial, which prepares the state that you start with. So you need to repeat this U initial, which prepares the initial state many, many, many times. So that's the reason.
You don't need those copies simultaneously.
Yeah.
Okay.
Yeah, that's right.
So with amplitude amplification, you start from the result of the previous circuit and then repeat that circuit?
Yeah, right. So this will be problematic. All right.
Yeah, so you construct a reflection operator with respect to the initial state. But how do you construct the reflection operator?
Yeah, you need to use.
Come from something else. So that is why in the unitary case, the oblivious amplitude amplification is so good because it doesn't involve a reflection operator with respect to the initial state.
Yeah.
And why that's the name oblivious. It's oblivious with respect to the initial state.
Yeah. That's a great point. That's precisely my next point. Okay. Well, so the question would be, still doesn't make sense because Hamiltonian simulation is doing this, but it works. Why? Right? Why is on the board? It's because we have oblivious amplitude amplification. This resembles amplitude amplification, but it do not involve the reflection around the initial state. So in other words, this is oblivious means that it is oblivious to the state that you start with. You do not need to require many of the state that you start with, which give you an exponential accumulation. But again, OAA really works if your underlying dynamics is unitary. If for general, well, it doesn't work. This is really the issue here. All right. I hope we are okay with the challenge. This is perhaps the most important slides of my tutorial today. Please.
Why can't you just use LCU or block encoding and then use OAA?
Yeah, that's precisely the issue is because now all of these A's are not close to unitary. Unitary, this OAA only works when it is unitary, when A is close to unitary. The reason is because when A is close to unitary, all of these are the same value. I can use that, okay, I boost them into 1, and all of them are uniformly boosted because there's just one value. I only need to show, okay, 1/2 or 1 over alpha is mapped to 1, and that's sufficient. However, you imagine if A is a general matrix, all of these singular values are different. And yet, afterwards, you still want to boost it in a form that all of the singular values are mapped uniformly. Mapping one value is not sufficient. Right? That's the reason. This only works for unitary. Yeah, very good question. Any further questions? Please.
So what happens here that leads to A not being close to unitary when yesterday in the lecture it was close to unitary?
Oh, it's because the Hamiltonian simulation yesterday and also the first part of today. This is the underlying dynamics, and this is close to this is a unitary. So when you do an integrator to this, because it's very close to a unitary, so everything should still pass through. So the numerical part here is a good approximation of the exact evolution, and the exact evolution is unitary, so everything is fine. But for general differential equation, the exact dynamics is not a unitary. So even if you have a good approximation, you are not close to a unitary. That's the difference. Please.
So I guess this doesn't work if the singular values of A are generally not 1, but if you have some sort of, is there situations in which you might have like a gap promise where they're larger than some value and you could just have a polynomial which amplifies close to 1, or?
Yeah, that's going to be what I'm going to mention as one of the possible solutions, but with some caveats. Very good question. Any other? Okay, so now I'm going to move on to address want to conclude by saying that the major challenge for non-unitary, this general ODE business is really that how do you go from short time to long time? So each of these integrator, you can do your whatever you like, your favorite. You can do truncated Dyson, truncated Taylor, you can do forward order, however you like. But the crucial challenge is really how do you go from this short time, piece them together into long time. So before I address the possible solutions to that, I just want to make a side note by saying that later I will mainly focus on time-dependent cases. You may wonder, what about time-independent cases? For example, if it's time-independent, on top of that, A is anti-Hermitian, such as negative I, H is anti-Hermitian, then you are actually back to the Hamiltonian simulation. Then we know that time-independent Hamiltonian simulation, QSVT gave you the optimal scaling. So this is an easy problem. Are you okay so far? This is what we talked about last time. And then you may wonder, okay, if the problem is time-independent problem, I have QSVT, right? QSVT is optimal for Hamiltonian simulation. Can I just use QSVT in a similar fashion and have a terrific algorithm for non-unitary dynamics as well? Right? That's a very natural question to ask. You agree with? But then you immediately might realize that QSVT, as the illustration purposes that I just read here, it really gives you this so-called generalized matrix function, which is not the matrix function. So if you think about if this function is e to the ta, these two things do not agree with each other. They are two completely different objects. Right? You can implement this guy, but what you really want is this guy. Are we okay so far? So that's why I read this as a very next exercise. It's just because you cannot do that naively. However, you may wonder, isn't there a really clever way so that maybe I can still somehow use the QSVT to do that? The answer is yes. So I can show you that. And the sub-circuit I'm going to borrow is this matrix inversion, which was talked about by Dong. The idea is that we are going to use this contour integral formulation, so complex analysis. Hopefully make my mathematical friends happy. So I'm just going to say, to write this contour integral, this Cauchy integral formula, you can sort of view that after a quadrature, what this is essentially doing is that I'm turning the exponentiation problem into a bunch of matrix inversion problem. Well, you may be like, well, still matrix inversion problem is not defined by the singular value transformation, right? Why is it helping? Are you okay with my logic so far? So now I'm turning this exponentiation problem into into matrix inversion problem. But still, matrix inversion, if I use QSVT, it gave me this generalized matrix function, do not really give me what I want. So let me just write it here and see what happens. Okay. So for simplicity, I'm just going to discuss maybe 1 over x, so that the generalized matrix function, alpha equal to 1 for simplicity. Can someone tell me what I should write here? Yeah, f of sigma, where f is this, so sigma inverse v dagger, right? Oh, what is A inverse? What's the relationship between the two? You dagger this. So for QSVT, although these two definitions do not agree with each other, but luckily if you are computing the matrix inversion, they can be linked together. But for other general things, you do not have this magic to happen. But nevertheless, you can utilize the contour integral formula, which gives you a pretty nice algorithm. Are we okay so far? All right. So now I'm going to come back to our challenge. So I have a general, say, time-dependent differential equation problem. I want to go from short time to long time. And we have seen that if I amplify using oblivious amplitude amplification, that's impossible because it's not necessarily unitary. If I use amplitude amplification at each of the time steps, well, that's going to be very costly. So the natural idea is that either I postpone this amplitude amplification, I deal with the success probability at the very end, hopefully I can get something. I will show you how we can do that. The other way is that you need to devise a new way that is maybe resembles oblivious amplitude amplification for unitary dynamics, yet still do what you want. So these are two ways, two possible ways to explore. So now I'm going to talk about the first way of designing first approach of designing quantum algorithm for differential equations. This is actually a very celebrated approach proposed by Dominic Berry back in 2014. And Dominic is one of the co-organizer of Workshop 1, so he will be around. And also Child's group and you in the audience. And these are many more of the very nice results. So this is sort of a teaser of Workshop 1, if you would like. So the idea is the following. I have all of these short time integrator. Well, how do I link them together? Well, each of them is basically linear system. Well, we know from those lectures, if linear system have larger dimension, it's still okay because it's log dependence. So I'm just going to concatenate all of the time step together, the initial time step, the second time step, so on and so forth, make it a very large vector. And correspondingly, I get a very large system that has all of the time step all together. This is possible. So here is an illustration. This is what you do. This is a first time step, which is long vector, second time step, and so on and so forth. And then you have a large linear system, and you try to use your best possible linear system solver to do that. Are we okay so far? All right. Now, what is the cost of the best possible linear system solver? We have seen from Dawn that it has linear dependence on kappa. Luckily, we have log dependence on n, and this S is for sparse matrix. This S enters the problem linearly because of the blocking coding factor, in fact. So now if you look at this problem, this problem is sparse? Is this matrix that I'm forming, this is no longer the A matrix that I start with. This is a larger matrix. Is this matrix sparse? Well, if A is as sparse, this matrix is still sparse, right? Very good. Second, this matrix size is larger. Is this still okay? Well, original matrix size is n. Now it's n times L, but it's inside of the log. It's still okay, right? And then the only leftover thing we really need to figure out is what is this kappa? In other words, what is this condition number? So in all of these algorithms, a crucial step is to give an estimation of this condition number of this new linear system that you just formed. And overall, you will apply QLSA using the optimal scaling one, which involves adiabatic quantum computing by what Dong has talked about. You will be able to achieve this scaling. If you use other naive, you will have a worse scaling compared to many of the parameters. But suppose you do that, you will have this many queries of L, which is this larger matrix you formed. Certainly, you need to discuss, given say input model of small a, how to create this large matrix, and also B, which is the right-hand side, you need to discuss, given the initial conditions, how do I create the right-hand side? But this is this many of queries to both of these oracles, and then you need to be everything precise. And now the leftover is really to estimate the condition number. It's typically in nearly all of these different methodologies, that the condition number will be inverse dependence on the time steps that you are having. For this forward Euler naive example, this alpha is exactly equal to 1. You can have other powers of alpha. This is what you can do. Please.
Is it a problem? Like, does delta t typically scales like something like 1 over norm a, right?
Yeah, that's right. That's right. That's right.
Norm a will typically be like have like a norm that's like polynomial in the dimension.
Yeah.
So then does that just like naively give you like an exponential cost for this algorithm because the condition number would also be exponential?
If you are assuming norm of A is not upper bounded by some constant that is polynomial in the number of qubits, as opposed you have exponential, then that is indeed a problem. But for sparse Hamiltonians, on top of that, well, if I have S sparse Hamiltonians, and each of the entries, for example, because the amplitude information are not that important, each of the entries, let's assume they are all bounded by 1, and then this upper bound is upper bounded by S, right, instead of N. So that is for sparse, so everything I'm talking about is sparse. Sparse is okay. For other, yeah, you need to be careful. Is there any other question? Okay.
Okay, I have one question.
Sure.
There's some quantum algorithms where the authors will be very clear about that if the largest eigenvalue divided by the smallest eigenvalue is bad, it's a bad fraction, then you will not get an exponential speed.
Yeah, that's right. That's right.
UCLA is one of the earliest papers.
That's right.
Is something like that going on here?
Yeah, it is possible. I will show you in all of these algorithms, there is a Q dependence, which states how large is your last time step versus the initial, and it has to be linear in Q by some lower bound results. So if your Q is gigantic, then that's problematic. So in all of these solvers, this Q is the essential parameter. Very good question. Any other? I will talk about what Q is. Yeah, thank you. Okay, all right. Well, so far seems to be done, but it's not done yet. If you do QLSA, you get this, but you don't get this. This is what you want. You have a larger superpositions, and this part is what you want. Naively speaking, suppose it's a Hamiltonian simulation, that all of these things has the same norm, all of them are normalized. Then to get extract information out from it, you naively speaking, the success probability is 1 over L, which is the size of this compared to the whole thing. However, for general differential equations, that may not be the case. You need to make sure this guy is not, say, exponentially vanishing in terms of this whole thing. So it's a naturally introduced parameter, which is what is called Q. Well, to fix this issue, typically you need to do so-called padding, which means that you put more last step here so that it boosts your success probability. So how many of those you need to put is typically where you need to introduce this parameter, what is called Q. This roughly tells you how large is the part that you need versus the whole thing. So this Q is really the intrinsic part of all of the differential solvers. It will have some dependence on Q. Please.
In this case, for this result, you don't need like an anti-hermiticity condition as you needed before.
Sorry, what is?
Like in the previous result that you presented, you needed A to be anti-Hermitian, but in this case, you don't need it for what you have.
Yeah, I don't need to, A needs not to be anti-Hermitian. So the previous time-independent case, I was just saying, if A is anti-Hermitian, then it's a Hamiltonian simulation. We don't need to do any of this business. I just use OAA, we are done. Yeah, very good question.
So for the first page, how does L scale with epsilon?
Yeah, that is dependence on your short-time numerical integrator. What is the error? What is the say the order of the error? Right. Other.
So for something like the heat equation, this Q will be like what, exponential?
Can be exponential, yeah. And for heat equation, there are actually work saying that there does not seem to be promising any exponential speed up by Ashley Maroon. I can send you the paper. Yeah.
Okay. Anything dissipative, basically?
Not necessary. Not necessarily. Well, not necessarily. Not necessarily. Here, for the simplified picture, I didn't talk about non-homogeneous term. For non-homogeneous terms, typically this you have a non-homogeneous term going on, and this is not.
There's a source that prevents it.
Yeah. And also, when we say vanishes, it really means that when t goes to infinity. However, in practice, you want to compute a finite t. It's not you want to compute t goes to infinity. For those, for differential equation, when t is already infinity, for many problems, there are equilibrium solutions that there are other ways to, equilibrium solutions can be dealt with as a static problem. You don't have to make the time evolution. Yeah, very good question. All right. Okay, so this is just one way. Okay, here I show you a generic results, which typically have some of the assumptions. All of these papers have different assumptions, but this is one of the assumptions. You need A to be sparse so that the previous sparsity applies. And if you have smooth and analytic, you don't have to have this assumption. But if you have smooth and analytic, you have very good convergence in the sense, mathematically speaking, the spectral convergence becomes the geometric convergence. So you have linear in terms of t, you have log in terms of the precision. And the dissipative is very generic assumptions. You do need some sort of dissipativeness in order to bound the condition number. If you do not have dissipativeness, the condition number can be a problem, can be large. Doesn't mean it's not bounded, but it can be large, can enter to here as well. And also, if you have time dependent, it typically assumes that this problem can be diagonalizable for all of the time, and the condition number of this V is actually have uniform upper bounds. This also enters in the condition number estimates, but if you can get a better condition number estimates, there are also, for time independent, we get a way of this capital letter T in this approach. They're possible, but this is a generic assumption. And then we also, as I said, that if the underlying A is really smooth and analytic, then everything, the spectral convergence really becomes a geometric convergence. Then I will have linear in T and log in terms of the dependence. This correspondingly basically assumes that the solution is super smooth in the sense that all of the derivatives needs to be remain bounded. You may wonder, what if I have say the solution live in a CK space, continuous differentiable up to case derivative instead of analytic, and then you will lose, well, it's very natural, it's spectral convergence, you will lose the geometric convergence. It will become a polynomial, a larger polynomial of T here, and you will have a polynomial of alpha here. So this is very natural for spectral convergence, what you can have. All right, so now, all the attention should be zooming into this Q, which seems to be, well, quite problematic. Then the question is this because of the implementation of the specific implementation of the algorithm, or this is something generic for this problem? It turns out the answer is very unfortunately, this is generic for the problem. Doesn't mean that for specific A, you cannot further improve. I will show you a further improvement. However, it just says that if you have a generic solver, this linear in Q is actually needed. So this lower bounds you can prove by a Grover search argument. What is even more interesting is that in this paper, and Liu in the audience, one can show that how many queries you need to curate the initial state preparation. It turns out in these formulations, you need this many queries of both A and the initial state preparation. However, seems that linear in Q should be sufficient. You should get rid of all of these for initial state preparation. Right? And then the very natural question is that then can we achieve the optimal state preparation? And with all of these similar assumptions going on, then can we achieve that at least? Right? Are we okay so far? Okay. And then I'm going to introduce there are two ways, at least, in the literature to achieve that. So to achieve the optimal in Q for dissipative system or satisfying all of these assumptions, you can achieve that. So this approach two, which is a way to link short time together into the long time, is going to go into the second idea, which means that I want to boost the success probability somehow at each of the time step. So imagine, what do I want? I really need a procedure that resembles OAA, but it works for non-unitary things. So concretely, what do we have? So let's still use the forward Euler as an illustration. This was the problem that I illustrated earlier. And this is the success probability, which is exponentially vanishing in L. You may wonder that, can we do better? Because this is what I have. Well, we know the best possible, if everything is perfect, the best possible some normalization factor I can hope for is of this form. Right? This is the upper bound of the underlying matrix that I'm having. If this is the case, then I do the multiplication, the product of the block encoding, I will have something like this. In a naive case, this almost look like, this will be very close because this is a good numerical integrator for this short time integrator. This can be approximation of this guy, which is close to e to the ta. What does that mean? Well, if A is anti-Hermitian, it's unitary, this is equal to 1. If it's dissipative, which was in our previous assumptions, anyway, it's bounded by 1. Right? So the nice observation is that if you do not have this, if you have almost the perfect one, it seems to be working well. It seems to be okay for dissipative and unitary dynamics at least. Dissipative means that the dynamics is upper bounded by some constant with some exponential and decaying terms, exponential decaying terms. Or it can be polynomial decaying terms. Yeah, very good question. Any other? All right, so on a concrete level, what we really need, this C means that this is a representative of the integrator. It doesn't have to be this specific form. This is just generic. So suppose your integrator have a block encoding factor of alpha, which is not perfect. If you were able to somehow to do it in a way to change the subnormalization factor to the almost perfect one, using a way that is oblivious to the initial state, such as what we can done by OAA, then you are fine. Are we okay so far? Okay. Now I want to change the subnormalization factor. I want to do from this to that. Can someone tell me maybe there is a technique on the board that I can use? I cannot use OAA because Kasi is not unitary. Maybe I can use this. Maybe I can use this, right? I can change the subnormalization factor. If this matrix function is a linear function with certain ratio in the front, and then I will be able to achieve that, right? So now, what I'm saying is basically, if I assume this ratio, all I need, I just do a QSVT. All I need is a polynomial approximation. Hopefully, it's with all the powers and so on and so forth. So the parity conditions can be satisfied. And then I need a polynomial approximation. This range is precisely because if you carefully look at the singular values range, it's bounded by this. So if there's no singular value, I don't care. I only care about the places where there are singular values. So this is all I need. I need a polynomial approximation. To approximate a linear function should be simple, right? This is what we can do. Please.
I guess, how do you find gamma in practice? Do you have access to norm C, I guess, or do you?
Yeah, you can have an upper bound sort of that, and then it's, yeah, very good question.
Yeah.
Please.
So what do you find out polynomial approximation for a linear functions? Should linear function already be a polynomial?
Yeah, that's a great question.
You need to be bounded by 1, right?
Yeah, I need to say this.
Oh, I see.
Yeah, I need to say this. Okay.
Like the polynomial to be bounded by 1 on the entire interval from
Yeah.
1 to 1, and also a polynomial.
Oh,
Yeah.
For some block encoding, alpha could scale with number of qubits. And in that case, the gamma could be really large. And then you're using
Yeah, you need to estimate in this QSVT what is the degree of the polynomial you use, and that will count into the cost. Indeed, yeah, it's an estimate to be done. Are we okay so far? At least, okay. So the reason, okay, now back. Why do I need a polynomial approximation? It's really because that's why I write it here. I have this normal assumption. If you look at these conditions, it's actually when you look at these terms, along these terms that we care about, it actually exceeds this bounded by 1 restrictions. If this is, that can be problematic. All right. Now then I just, but I shouldn't worry too much. It's just a linear function. I can construct a polynomial assumption, which hopefully exactly give me something that is upper bounded by 1. However, if a numerical analyst, you immediately realize there is an issue of Gibbs phenomenon. You cannot precisely reach that point. There has to be some overshooting so that you need to sacrifice something. So instead of, if you make a polynomial assumption, it's impossible to get perfectly none of the, a uniform bounded. There will be a Gibbs phenomenon. There will be some overshooting. So you need to sacrifice a delta, which pull down this a little bit so that the condition is satisfied. So this is very crucial here. So far so good, and then we find the polynomial approximation, which is, and then we get a way of simply of amplitude amplification. This can be is called uniform singular value amplification. Is because you uniformly boost all of the singular value by the same rate, and it turns out you can prove a lemma that the degree is of this kind. All right, now this is just a generic way. You can use any short time integrator. I'm using this time marching strategy. So I just show you the generic results that one can have is that you have linear in Q, this is expected. Unfortunately, you have T squared. But luckily, you don't need to assume the A is analytical smooth. Bounded variation is going to be sufficient. However, you may wonder, if IA is really analytic, you use this boosting strategy, can you get linear in T? can you recover the linear in T? The answer is unfortunately you cannot. This T square has to be there if at each of the time you are making some, but it's still polynomial in terms of the T. So this is the scaling you get. And for dissipative dynamics, and you get linear in Q of oracle preparation. So as you see there, you get a log dependence on the scaling, which is fairly good, linear dependence and linear dependence in Q, which is fairly good, but this T scaling is not the best possible one that you, so this is not a complete story. Are we okay so far? Okay. Now I'm going to introduce the third way of piecing together this short time evolution to long time evolution. So the authors are all in the audience, Anne and Lin and Liu. Please feel free to chime in if you like. So the idea would be, if it's Hamiltonian simulation, I just use OAA. I piece everything together, there shouldn't be any problem. If I just use OAA, I do not suffer from T squared, right? I'm okay, I will just be okay with T. I don't introduce this T square factor. And then how can I change non-unitary dynamics into Hamiltonian simulation? It turns out this is very nice, again, complex analysis, very sort of built from formulas that they were able to prove, is that you can change this. There is some dissipative assumptions again, and you can, but under this assumption, which is assumed anyway for all of the existing algorithm, you can show that this is actually the case.
Since you already have a minus, LT should be positive.
No, I didn't have minus in my original equation, so that's why I said I did. My equation is U dot equal to AU, so that's why.
The time ordered.
Oh right. Right. This should be positive. Thank you. This should be positive. There was a typo. Thank you. So you look at this equation. What is really remarkable is that there is an integral which you can use again by some numerical quadrature and then do a LCU. We are familiar with this business, right? And then this will be some chosen case. These are just going to be some constants. And you look at each of these, what do you have? Well, you have Hamiltonian simulation. This is because you can decompose A into this Hermitian part and the anti-Hermitian part. Well, both L and H, you can easily check they are both Hermitian. They're both Hermitian. So this is precisely the Hamiltonian simulation. And then you have two Hamiltonian simulations. You can somehow use a chotter to do this one, do that one, combine it using maybe a high order chotter, and then you can perform a Hamiltonian simulation of the whole thing. So this is a high level what the idea is. So it's a sorry?
Does it come from a contour integral?
Yeah, exactly. It can be proved by a contour integral and some Jordan lemma business. Yeah. Okay. And the generic results for dissipative dynamics would be, this will be the scaling we get. We are almost linear, and here we also don't need the, say, A to be analytic. And we are almost linear, but the precision is not log in terms of the precision. So none of this algorithm is perfect. That's why there's a lot of room for us to discuss together. There are always some cons and pros, but this is and this also remarkably achieve a optimal cost of the state preparation for dissipative dynamics. All right. Okay. So I think I'm pretty much.
Another question for that last one. So you're having this extra assumption of the real part being negative definite, right?
Yeah.
But for arbitrary A, you have no guarantee.
Yeah, that's right. Yeah, that's right. However, this sort of dissipative assumptions is needed for all of these three algorithms. Well, in the second algorithm, you do not need that, but then the operator norm of e to the ta will come into the cost. So somehow it needs to be.
I mean, that was the point I was worried about before with your magic formula that e to the ta is uniformly bounded.
Yeah.
That's not always the case, right?
Yeah, that's true. If that's not the case,
that's kind of the same assumption you're making.
Yeah, if that's not the case in the second algorithm where we boost the success probability at each of the time steps, you have e to the ta entering into the cost. You multiply e to the ta norm to the whole thing.
Yeah.
Yeah, that's. Yeah.
So to satisfy LT to be positive definite or negative definite, you can add a shift, but of course you need some a priori knowledge.
Yeah, that's right.
Assumption. But indeed, this one has a little bit stronger assumption because it requires, after the Cartesian decomposition, the real part is positive semi-definite, which is a stronger condition than earlier result, which only requires the eigenvalues to be on the left half of the complex plane. So there's a slight difference between.
Yeah, that's right. That's right. So finally, I just want to mention a little bit, maybe this is again a teaser, hopefully for workshop 1, is that so far everything I talk about, the differential equation solvers are all generic, so for generic A's. It doesn't mean for specific A, if there's further nice structure to the problem, you cannot get further improvement. One particular example I think worth mentioning is a recent paper by these number of people. Barry, workshop 1 organizer, and Kausari and Soma will both speak at workshop 1, and Viv is a workshop organizer of workshop 2. So the point is that, just a simple illustration. If your differential equations have certain conservation laws, one simple example is maybe it's a Hamiltonian flow, where it's just simulating a harmonic oscillator. For simplicity, I'm ignoring all of the math, but there are general formulation. But the point is that I have some conserved energy, and everything is in a quadratic form. The number of particles can be gigantic. It turns out, why is this so nice? It's because you can reformulate the Hamiltonian ODE, which is second-order differential equation, into this linear first-order differential equation, and you quickly realize that the L2 norm of this vector does not change because of the conservation of energy, right? So if the norm does not change, if we do not lose information. So this is a sort of, but this is not generically true for arbitrary A's. This is just true for this particular case. Then for this particular case, since there's no norm losing, then sort of informal idea is that you can map it into one Hamiltonian simulation and time-independent one. You can use your best algorithm, say QSVT. And what is really interesting is that for this problem, even if you are focusing on a very easier problem, you can still show it's BQP hard. So this is sort of just some teaser of what we might see in the later workshops. So with that, I just want to conclude everything I would like to discuss.